Good morning, fellow mathematicians. Welcome back to another. This video has been sponsored by Diotica.com. Oh boy, that hurt more than expected. I challenge you, Black Pen, Red Pen, and all the other math YouTubers, especially this fucking bald guy, mathologist is his name, right? To bash their heads against something, I don't know, wall, blackboard, whiteboard, as hard as they can. So if you're a manly math YouTuber, then I hope you are up to this challenge. Also you, Simon Clark, even though you're something like a physicist or something, bash your head against a wall or something, I don't know. We are going to solve this integral today. For the third time, but this time using Laplace transforms. I like presenting you guys different approaches to same problems. So here we go, here's the third time integrating something once again. I'm the guy who integrates stuff. So let's go ahead and get started. So the good thing is we're integrating from 0 to infinity, so that's quite nice. So let's just introduce a new parameter right here, t. Without any restrictions, we are going to assume it's greater than 0. It's the unit of time. Let's say it like that. It's strictly greater. So some I in terms of t is now the improper integral from 0 to infinity of sine squared t times x over x squared plus 1 dx. And just like I said, let's apply Laplace transform to this time-dependent function. So the Laplace transform of I in terms of t. What is that? Well, by definition, it's just the improper integral when t goes from 0 to infinity of I in terms of t e to the minus st dt. Now, naturally, we should plug in the definition for I in terms of t. So now it's the improper integral from 0 to infinity, and then improper integral when x goes from 0 to infinity of sine squared t times x over x squared plus 1, and then a dx in the normal case, but e to the minus st is just a constant in terms of x, so let's bring it to the side, my boys. E to the minus st dx dt. And now, without any restrictions, we are going to interchange those two infinity boys, just because we can. Pure math guys hate this person here. Call this number to learn how he interchanges those integral signs without any restrictions. So let's do it. Now we have the improper integral when x goes from 0 to infinity of, I'm going to factor out the 1 over x squared plus 1 term, because in terms of t it's just a constant, so let's bring it to the outside. And then the improper integral when t goes from 0 to infinity of sine squared t times x e to the minus st dt and then dx. And if you've got a sharp eye, you might notice this whole integral is just the Laplace transform of sine squared t times x. And this time I want to make sure that I don't do any mistakes at the first try recording this video. So now we have the improper integral from 0 to infinity. Also we know what this is right here, link in the description as always. 1 over x squared plus 1, and also times. So up here we have 2x squared over s squared and the factor of s, don't forget that. And also we have plus 4x squared dx. And quite magically, this and that is going to cancel out, and we can bring a factor of 2 over s to the outside, and let's see what we end up with. So in conclusion, the Laplace transform of I in terms of t is now nothing other than 2 over s times the improper integral from 0 to infinity of 1 over x squared plus 1 and then times 1 over, let's put it together, let's put it in parentheses, so s squared plus 4x squared dx. And as sad as it is, we have to use partial fraction decompositions now. Can't do anything about it.
NANI?!
I am the partial fraction decomposition cat. No one needs this filthy mathematics. Vanish, you monster!
So we are done with the shitty math memes, and here's our final expression. So we have this partial fraction decomposed, and I factored out all the constants and stuff like this, brought it to the outside, and also I have used the linearity of the integral to split this up. And now we can integrate those two terms quite easily, to be honest. So this right here is just the inverse tangent of, well, x in this case, from 0 to infinity. And this right here, well, is close to the inverse tangent, but we have to factor out a factor of 4. So in conclusion, this right here is now 1 over 4 and then dx over, don't forget your integral later on. We have an x squared now plus s squared over 4. We can rearrange this to s over 2 but the whole thing squared. So plus s over 2 but the whole thing squared. And you might notice this and that is going to cancel out, and this leaves us with some kind of inverse tangent. So the integral of this thing will then be, okay, let's conclude. This is just 2 over s, don't forget your minus sign, I'm going to put it here, minus 2 over s, and then we have the inverse tangent of x over s over 2 from 0 to infinity. And now let's see. Well, inverse tangent of 0 is always going to be 0, so that's nice. So those two terms are going to vanish. And also, inverse tangent when x goes to infinity is just pi over 2. So that's pi over 2 and that's pi over 2, and let's see what we get in the end. Now we have 2 over s squared minus 4. That's supposed to be a 4. I'm too dumb to write. And also we have. So this first term leaves us with pi over 2. And the second term is minus 2 over s and then pi over 2. This and that is going to cancel out. And that's quite nice. So let's see, in conclusion, what do we have? Well, we can factor out a big pi in here. So we have 1 over s squared minus 4. And also minus, and we have 1 over s squared minus 4. And once again we have to use partial fraction decomposition on both of those terms, because remember, we are only at the Laplace transform of I in terms of t. So in order for us to get to I in terms of t once again, we have to use the inverse Laplace transform on the Laplace transform of I in terms of t. And in order for us to correctly do that, we have to use partial fraction decomposition here. So guys, I'm giving you 3 seconds to prepare for a new meme. I don't know what it is right now. 3, 2, 1, meme! We are nearly done. Nearly. We have used partial fraction decomposition. Those are all the terms, and I have factored out a 1/4. So we are ending up with this right here. All we have to do now is simplify a little bit and then use the inverse Laplace transform on the Laplace transform of I in terms of t. Oh. So let's go ahead and do that. So at first you might notice something. I have simplified this right here a little bit. So 4 is nothing other than 2 squared. And the good thing is this is the difference of 2 squares. And we have the same denominator here. So we can add those two fractions together to get s minus 2 over this chunk. But the difference of 2 squares, there's a nice formula for that. This here is nothing other than s minus 2 times s plus 2. So in the numerator we have s minus 2 as a factor, and also in the denominator. So we can cancel those out. And those two added together are just 1 over s plus 2. So let's conclude. We end up with pi over 4. And then we have 2 over s squared minus 1 over s. And we also have positive 1 over s plus 2. And just like I said before, let's use the inverse Laplace transform on the Laplace transform of I in terms of t. That's a nice expression. And this is going to give us an expression for I in terms of t. Well, using the inverse Laplace transform on this chunk right here, well, pi over 4 is just a constant, and we can make use of all the identities we've derived before. So 2 is just a constant, we can bring it to the outside. So we have a factor of pi over 2 then. And the inverse Laplace transform of 1 over s squared is just a t. So our first term is pi over 2 times t. Next term, pi over 4 is a constant, bring it to the outside. Inverse Laplace transform of minus 1 over s is just minus 1. So we have minus pi over 4. And the last term, pi over 4, constant, bring it to the outside. Inverse Laplace transform of 1 over s plus 2 is just e to the minus 2t, if I remember correctly. So we have plus pi over 4 e to the minus 2t. But we are not completely done yet. You might remember something crucial. This is just the solution to I in terms of t, but we wanted to solve this originally. How can we do that? Well, let's set t equal to 1. That is going to give us the original expression. So let's go ahead and do that. So the solution to our I is just I in terms of t equals to 1. That was supposed to be a parenthesis. Never mind. And this is now pi over 2 minus pi over 4 plus pi over 4 times e squared. Because t is just 1, e to the minus 2 is just 1 over e to the second power. Well, pi over 2 minus pi over 4 is just pi over 4. So we end up with pi over 4 plus pi over 4 times e squared. And then we are done. So that's actually the solution to our integral. We've derived this before 2 times. And that was the third time, I guess. If you did like this video, please like and subscribe and recommend me if you like. If you want to see me doing more sexy math memes, then make sure to support me on Patreon. YouTube isn't hurrying up monetizing this channel, and I would like to get at least a bit of revenue for what I'm doing here. So if you want to support me at least a little bit, feel free to spend some bucks on this enthusiastic little guy right here. Up until the next video, have flammable day, I guess. I'm wishing you the best day possible today. See ya. Hey guys, it's me once again. We just saw each other like 1 second ago. Don't forget to check out diodica.com. They are a sponsor of mine and they are a team of really nice people. So if you want to get some Flammy laser, burn something down, burn your house down, burn your mother down, I don't care what you want to burn down. But if you want to get a laser that can burn down things, feel free to check out their website. They are making lasers accessible to everyone and it's quite nice. I'm going to receive mine soon. They have already shipped it away. I'm so excited for this laser. I want to burn some stuff down. Check them out. They are cool. See ya.